Hi, hello everyone. This is Dr. Abdul Pasha. So we are dealing with the course Power System Operation and Control. So here it is about load frequency control operation. So earlier we discussed some points in the load frequency control, how it will be managed. And here we will continue the same session with the second case, that is load frequency control operation. So coming to load frequency control, how we supposed to define this case means, this is a system that regulates the flow of power between different regions for an interconnected power system network. So here the purpose is to maintain the constant frequency. So load frequency control is an important because it helps to maintain the voltage and frequency regulations. So which will divides the load in between the generators, control tie line interchange schedules, and maintains the power balance in between the interconnected areas. So likewise LFC will take place. So here is to maintain the constant frequency. So here load frequency control can be treated as a key parameter for the reliability of a power generation system. So it involves automatic gain control, that is AGC, and it also involves with the steady state error concept to avoid frequency variations and make the system to be stable. So generation of electricity is being done by both renewable and non-renewable energy sources. So thermal generating units are conventional method for the electricity generation, in which fuel like we are going to use as coal, nuclear energy, natural gas, biofuel, biogas. So these are some of the natural fuel cases which will be burnt in a boiler case. So boiler of a generating unit is an extremely complex system. So but in the simplest form, it can be understood that as a room whose walls are made with pipes in which there is a continuous flow of water. So thermal energy is released by burning of the fuel inside the boiler, so which is going to be transferred to the water. So what happens with this means, in this process water is going to be converted into the dry saturated state of high pressure, and which will be considered about 150 kS to 380 kiloseconds. So that is depends upon the design considerations. So, and which will be operated with high temperature, that is about 530 degrees centigrade to 732 degrees centigrade. That will depends upon the design case. So here saturated steam is given to the turbine, where it expands and its temperature gets decreases. So in this process what happens means, steam is going to transfer to its thermal energy to the rotational energy case of the turbine shaft. So the flow of steam into a turbine is controlled by the control valve, which is controlled by the governing mechanism of the turbine case. So the active power flow of the turbine is controlled by the governor system. So turbine is coupled with a synchronous generator case. So that synchronous generator is going to convert the mechanical energy of the turbine into electrical energy case. So synchronous generators generate power at lower voltages, which will be ranges from 11 kV to 26 kV of voltages, and which operates at nominal frequency values. So voltage is here going to be stepped up to a value of 220 kV to the 400 kV and to the 765 kV. So from 220 to 765 kV it may happen. That should be done by a generating transformer for transmission to the grid case. So this process or this complete system is termed as a generating unit, in which the power system studies are going to be takes place. So in this load frequency control operation, we supposed to discuss about turbine governor mechanism control. So what is this TGC or turbine governor control? So as we earlier mentioned that governor is going to regulate the flow of active power into the turbine. That is done by controlling the control valve. So a hydraulic governor can be modeled as integral controller which takes the feedback from the actual speed of the turbine. So here we are representing a functioning of the governor in the speed control module. So see here, this is the turbine mechanism. So here the control blocks are connected to the excitation of the turbine case, and this turbine is coupled by generator input section. Here we are collecting our output. So whatever the control over, that should be done at the primary section. That means from the input section we are going to apply reference speed, and it should be operated with gain factors k and internal factors of 1 by s with the delta y. And here we are going to apply our required amounts of steam to this turbine. This will regulate the flow of speed of this turbine case. This control is going to be taken place. That means the output is generated from the secondary section. So this block is again represented here as delta omega r, and this control block is connected to k and it is maintained by 1 by s. So this is taken in the written path and operating as r, and this block can be simplified with the delta omega r to the minus 1 by r case, and this summation function of the transfer function as finally writing to the coefficient as 1 by 1 plus stg case. This is represented with the delta y case. So here actual speed of the turbine is compared with the reference speed. So that means corresponding to the nominal frequency is considered, and the error signal whatever delta omega r is then given to the governor case. That means based on the error signal, governor opens or closes the control valve position. So when a positive error is received means actual frequency is more than the nominal frequency. So in this case, governor closes the valve to a little bit, and vice versa the happens will takes place. So R is the droop setting of the governor, and generally it will be varies from 3% to 8%. So here the capital R value is taken as per unit change in frequency. That means per unit change in power also going to be takes place for capital R. So droop settings are decrease in the setting value is required for a stable parallel operation of various generating units. That means which is going to determines the load sharing in a control area. So the unit with the smaller drop value will share the more load case. So here it will come across with one more concept called control area. What is this control area means? In a power system network, many generating units and loads are going to be connected to the distributed manner. That means to maintain the stability case, total grid is going to be divided into various control blocks, primarily based on the geographical locations. So for effective load operation, for flow calculations, and subsequent control of frequency and power balance is going to be taken place. That means in a control area, more than one generating unit as well as loads are considered. So that means some of the objectives are defined to achieve the dividing the power system into smaller control areas. So here the load frequency control helps to maintain the frequency of the grid. That is by load frequency control methods. We are going to consider some simple methods for making load frequency control operation as a smooth. So it is discussed here with some considerations. So determination of schedule interchanges may take place. That means in a control area for a given particular geographical location, there is a possibility that generation is less than the load demand. That means hence the power flow is into the control area from the nearby control areas by tie lines, and from that input sections are considered to make the schedule interchanges. So what is effective load sharing? Effective load sharing means whatever the load demand reduces in the night time and is at peak at evening time and morning time, then by dividing the power system into smaller control areas, it becomes very easy to determine the load sharing by different units as per the projected load demand case. So during that day, in accordance with their capacity and for calculation of the scheduled interchanges, we will make the control area cases. That is called effective load sharing from the power system network. This may going to reduces the load demand. And we also go with the power balancing in this case. That means at any point of time, so electric energy produced must be considered by all the connected loads. That means as it cannot be stored usually. So electrical energy is a real-time energy process. That means balance of power is supposed to be achieved always there in the electrical system. So this balance of power can be denoted with the power generated, denoted with the PG is equals to load demand PD, that is PG equals to load demand PD plus one of the transmission losses. So this makes the power generation coefficient. This is one of the equation which will specifies or determines the balance of the power. So here transmission losses are generally ranges from 2% of the generated power, and so it will be neglected them for understanding the subject topic, that is frequency control. So we can say that power generated is meeting to the load demand case. That means PG is going to approximating to the load demand case, PD case. So likewise it is going to meet us with only 2% of the expected transmission loss. So the frequency variations also we may observe here in a grid. Many industrial loads, so like house loads, lightning loads, these are connected. So these loads are switched on or off without any intimation. Hence the load demand always fluctuates in a power system network. So whereas a generating unit is said to generate a particular power and it cannot change the generation very quickly. So as it is a mechanical system, so there are always minor gaps in between the demand and the generation. So these minor deviations don't result in the significant change in the frequency due to the large inertia of the power system network. So coming to this frequency control operation, the load frequency control or frequency control is the system by which the frequency of the grid is maintaining or brought back into the normal value after demand generation gap. So frequency control of the whole power system is done by generating units. That means there are two types of frequency controls usually, primary frequency control and secondary frequency control. So coming to primary control, which will corresponds to the speed control mechanism of an individual unit, whereas secondary control means it is done by the coordinated control of various generating units which are located in different control areas. So coming to primary frequency control, at unit level, the frequency control is done through the governing system of the turbine. That means speed control of the governing mechanism has already been represented, but each generating unit increases the steam input into the turbine by seeing the difference in the frequency. That means complete primary frequency control loop of the generating station is going to be represented, which will make the primary frequency control operation in the power system network. So this is denoting how primary frequency control is going to be done. So here the referred power is given, reference power, which is connecting to the block to the governor mechanism. This mechanism is represented with one of the function 1 plus STG. It is connected to one of the valve. Here we are going to apply the amount of steam. From this, it is connected to the turbine case. Here the turbine is represented with one of the transfer function 1 plus STT, and this block is going to connect it to delta TM mechanism. So here tie-line power with one of the load is connected here in this block. So system inertia is generated with Kp by 1 plus STP. So this block is connecting with the delta F, change in frequency. As one of the drop is expected with 1 by R, this is connecting back as feedback to the power source. So likewise, primary frequency control operation takes place for this system. So, however, the primary frequency control action will result in a steady state frequency deviation. That means, based upon the governor grouping characteristics and frequency sensitivity of the load, this is because all individual units are running on speed control module. That means this is to increase the frequency irrespective to the location of addition of new load or how much load is added to the system. That is going to be evaluated. So without such assessment, it is impossible to bring power balance. That means in the system, the frequency deviation will persist. So this may usually happens. So after primary frequency action by all the units under steady state deviation conditions, the frequency may be positive or negative, or it may be both. It may take place. So secondary frequency control. What happens with secondary frequency control means restoration of the system frequency to the nominal value going to be required to the secondary control, which actually sees that location of new load and adjusting the load reference is a set point of the selected few units only. That means whenever the load is going to be increases in a particular control area, generation must be increases by generating units of the particular area. So this is as to keep the demand generation balance at control area level and a scheduled interchange in between the control areas in their pre-decided ranges. So likewise, secondary frequency control operation is going to be takes place here. Next, automatic generation control. What is AGC? So earlier we discussed some keynotes about automatic generation control. So for achieving better in this, few units in each control area are assigned for secondary control, and in their control loop a frequency bias loop is added, so which gives the corrective signal for increase or decrease of the generation. That is based on the real-time load flow calculations. So this is also known as automatic generation control. So coming to this, after revised load, set points are given to each units. They start to act to achieve their revised generation schedules. That means in individual units, there is a mechanical system for electrical power generation. Hence, it is going to take approximately 25 to 30 minutes to achieve the generation as scheduled by secondary control. So after generating stations achieves the scheduled generation, so power balance is once again reinstalled and frequency comes into the nominal value case. So this is the block diagram showing automatic generation control. Initially it will be supposed to be achieved with power reference, and here it is connected to the governor block, and this governor block is followed by steam input that is connecting to the valve section, and here turbine is connecting with 1 by 1 plus STT. This block is connected to the load means that is connected by delta TM, and this part is separated by system inertia constant as Kp by 1 plus STT. So here this path is connecting as one of the feedback path to the B section. In between drop is considered here. That drop is again compensated with the reference power, and the frequency bias is supposed to be taken place with B with 1 over the control integral action. That means minus Ki by Sk. So likewise, automatic generation control will operate as a feedback path from a system inertia to the frequency bias conditions, which is going to be integral, and the droop in any value is going to be given feedback to the power reference. That will nullify its droop, and it is connecting to the run the system as usual. So here the overall response of the system with the primary and secondary frequency control can be understood by one of the simple graph. So this may called as primary and secondary frequency control graph. So here what happens means the natural response of the power system is represented with one section as A, and the primary frequency control is another represented with another section as B. secondary frequency control of AGC is represented with C. Like the D will be followed, and here one of the section delta P representing sudden addition of the load leading to the demand generating, that will ready to mismatch, and here it will follows and it will rises like this. And coming to the nominal frequency values, which may usually drops in this section and follows the reference path, which makes a steady state error after primary frequency response deviations with the delta F. This may also represent one of the change. And here nominal frequency again may be considered with a frequency recovered to nominal value, and the power system is found to be power balance with additional load case. So this is, here it is with 5 seconds and here it is considered under 30 seconds. The whole process will follow still 30 minutes of the time. This combinedly follows primary and secondary frequency control graph. So here the number of sections which are provided A, B, C, D may be divided into each pair. The pair A to B, which is that system was running at a power balance under state prior to the point A. So here it is prior to the point of A. So at that instant of point A, suddenly load is increased from P0 to P0 plus delta. So there is a time delay approximately 3 to 5 seconds for the governor to come into the action case. Hence, at all the time stored kinetic energy of the rotor caters to the excess load, and in this process speed gets slow and frequency decreases up to the lowest point, that is F1. And at the pair of B to C, after about 5 seconds, the governor starts speed control action and the steam input starts to increases and the speed of the rotor is going to be increases. So this stage lasts about 20 to 25 seconds, which will depends upon the dip of the frequency. That means, as mentioned earlier, there is always a steady state error delta F in the frequency after primary control action. In the pair of C to D, after stabilization of the frequency, secondary frequency control starts and selected generating units of each control areas, they may goes to increases or decreases their generation based on new load reference that may ready to incorporate the frequency bias. That means this action may take in several minutes as a generating units, which is having the design ramp rate for reducing or increasing the load factor. So after this process, the action scheduled here interchanges will also comes with the calculated value. So the power system finds the new power balance and the nominal frequency is going to be achieved. So here with one of the controller is introduced for making the single area to be smoothened, that is called proportional plus integral control. So by using this control strategy, we can make the speed changer to be commanded by signal obtained by first amplifying and then integrating the frequency. This is represented with the delta PC, that is minus Ki integral of delta F dt. So this is representing one of the proportional plus integral control area action. So here the unit of K is per unit megawatt. That means per hertz and per second also considered to make the integral action. So integral control is giving rise to zero static frequency error, so which may following to the step load change. That means single area load frequency control system with the PI control actions is ready to nullify the errors produced due to this action. That means integral controller is going to make Ki by S, which is connected to one of the block delta PC of S, and this block is connected by one of the transfer function suitability 1 by 1 plus STG into 1 plus ST2. So this is connecting to the one of the control block delta PDS. So this is followed by the section KP by 1 plus STP and it is connecting to delta FS. So this path is returning here as 1 by R, as it will controls the drooping value and this looping value again is nullified here and fed back to the main bath. So here this control over is connected with one of the frequency sensor as one. This makes the frequency sensor. So whatever the system we shown, that will now modifies as to proportional plus integral controller, which gives zero steady state error. So here the value of steady state error is 0. That means dynamic response of load frequency controller with and without integral action is ready to take in place. That means this is considered with one of the steady state error, and the operation is maintained with integral control action and without integral control action. In between these two regions, we may expect it with the steady state error. So this is with one of the time lapse, and this change of frequency is with the delta f into 10 power minus 2. So these values may varies from 0 to -7, and here till 20 it may reach. So here this load frequency control and economic dispatch control is represented with one of the two coefficients called EDC and CEDC. That means economic dispatch controller and central economic dispatch computer. So what is happening here means integral controller is designed with Ki by S connecting to the control block, and this is followed to the speed changer section. That speed changer is connected over governor mechanism. This governor mechanism is connected over turbine case. Finally, it is connecting to the generator excitation system. The path is feedback to one of the local EDC, that is economic dispatch controller. So any error produced will be nullified here in the control block, and this path of response is connecting to the integral controller. That means desired power is achieved from the desired received from CEDC case. So here the load frequency control will changes the speed changes setting for the governor of all the generating units of the area case. So what is happening with this means frequency is returning to the scheduled frequency value. So signal whatever desired is calculated by the central economic dispatch computer. That means CEDC is achieved and is transmitted to the local economic dispatch control, that is EDC, and that may be installed at each station with a given suitable value. So load frequency control of a two area is an interconnected system. That means an extended power system can be divided into a number of load frequency control areas, which may be interconnected by means of tie lines. That may be considered a two area case connected by a single tie line, that may be shown here. This is control area 1, this is control area 2. They are both connected by tie lines, control area 1 and control area 2. So here power transmitted from the area 1 is given with the tie line power 1, V1 V2 by X12 sin delta 1 naught minus delta 2 naught. This is representing one of the equation. When delta tie line power is considered in per unit, then T12 of delta 1 minus delta 2 is considered. Here where T12 is V1 V2 by PR1 X1, that is cos of delta 1 naught minus delta 2 naught is considered. This factor is called as synchronizing coefficient. Synchronizing coefficient. T12 is called as synchronizing coefficient, which is considered in between the difference of delta 1 naught to the delta 2 as cos of delta 1 naught minus delta 2. So this changes in angle can be expressed as the integral of change in frequency value, that is delta p tail n. So 2 pi t21 which is the product of integral of delta f22 dt minus delta f1 dt. So where t21 equals to v2 by v1 in by pr2 x21, which is as a factor of cos delta 2 naught minus delta 1 naught. So this is about T21 case, PR1 by PR2 into T12, which is equating to A1 to T12 case. So in general load model case, the incremental power balance equation of area usually represented as delta Pg1 minus delta Pd1. So this is equating to 2H1 by F1 naught into d by dt of delta F1 plus d1 delta F1 plus delta tie line power. So here the block diagram model of a two area interconnected system is shown. This will be connected by various blocks with B1 section and here B2 section. That means here it is connecting to one of the block Ki1 by S, which is making the control over here with one of the transfer function 1 by 1 plus STG1 into 1 plus ST2. So this block is connecting to the delta Pg1 of S. This is representing the tie line power and it is connecting to reference of delta PD1 of S. This block is suitable to Kp1 by 1 plus STP1. That means the intersection of these two sections are connecting to 2 pi T12 by S. Whenever there is a changeover frequency happens, then delta F2 of S may come into contact. This secondary section is connected by Kp2 by 1 plus Sp2 and this block is connected over by this control section as a tie line power 2 and this is connecting to 1 by 1 plus STG2 into 1 plus ST2. So this block is returning to the path as K12 by S as delta PC of S. So the drop across this may be feedback as 1 by R1 here. And here the drop is feedback in the second section as 1 by R. So any error expectancy that may be connected as feedback here also. So this may be rectified and the path again continues to function. So static response of two area system is considered under uncontrolled case. That means what is happening in uncontrolled case means response of the two area system with fixed speed change or positions are considered. So what are these fixed speed change or positions means? Delta PC1 equals to delta PC2 equals to 0. That means they are assumed that the loads in each area are suddenly increased by constant incremental steps. So that is delta PD1 equals to M1 and delta PD2 equals to M2. Likewise, they are going to be represented. So the steady state frequency usually represented with the delta F as M1 plus M2 by beta 1 plus beta. This is in hedges and where beta 1 is D1 plus 1 by R1, beta 2 is D2 plus 1 by R2. So these are one of the two coefficients of beta. So the line power deviations may also obtained here as a P12 as a tie line. The delta P21 tie line as B1 M2 minus delta beta 2 M2 by beta 1 plus beta. This is considered under per unit value in megawatts. This is another equation representing tie line power deviation. So this deviation may be existing from the initial condition to the extended value. So the dynamic response of two area system is considered under uncontrolled case, though that dynamic response of the two area system is based on the particular assumptions. That is, it may be considered with the case of two equal areas, that is considering the turbine controller fast relative to the inertia as part of the system with GH equals to GT equals to 1. So here we need to neglect the system damping. That means we need to assume that load not to vary with the frequency. That is D1 equals to D2 equals to 0. That should not vary to the given frequency. We need to derive the expression for the tie line from the block diagram as a delta P tie line. So pi F0 by T12 by H into delta PD2 of S minus delta PD1 of S by S square plus F0 by 2RHS into S plus 2 pi F0 T0 by H. This is representing another equation. So that observations we may conclude that system damping is strongly dependent on the one of the parameters. So what is happening here means for low value of D, the value of the parameter is increased and thus it is achieving the high damping case. So this is obtained, therefore D parameter fills an important damping function. That means in interconnected system it is going to be taken place. So coming to the damping cases, as there is a change in frequency function as delta f of t, It may be represented with f of 1 of t with changeover and f2 of t with changeover. These oscillations may be reset to the with reset control and without reset control. So with reset control, the variations may be taken place at this location. Without reset control, this may be reached at this location. That means f2 1 of t is achieved with this function. So the uppermost layers representing the variations of the frequencies under f1 of t and f22 of conditions with nominal values. These nominal values may be fixed at this location with the delta f0 case. The controlled case is obtained if frequency of two areas is to be controlled. That means static frequency drop is just one half of that isolated operation of the two systems. That means if there is any change in the load in any area, half of it will be shared by the other area cases. Likewise, we may reach controlled case. So it is found that if a load changes in area, the frequency and interchange errors in that area have the same sign while these opposite signs for the other area. That means the relative signs of the frequency and interchange deviations helps to identify the area where the load changes are expected going to be changes. So here are some previous gate asked questions with the two generating units. They are supposed to be rated at 300 megawatts, 400 megawatts. They have governor speed regulations about 6% and 4%. So that should be from no load to full load case. So both the generating units are operating in parallel to share a load of 600 megawatts. So assuming that free governor action is going to be taken place, so load is shared by the larger unit section with megawatts. So that is X be the frequency variation at which a 600 watts load is going to be meeting the conditions. We need to calculate the frequency variations as the power is fluctuating from P1 to P2. Here it is with 300 megawatts, here it is with 400 megawatts. The frequency variations in between these two powers are considered under various sections A, B, C, F, G, D, E, F. And during these conditions, how the load frequency variation, we need to divide the subsections according to this given values. So with this similar triangles method, we need to consider the separate sections of the triangle AED as well as ACH. So here it is representing with a 300 power and here 400. So from this portion we may treat FB by ED, here BG by CH, that is equals to AB by AC case. That AB by AC case is going to be given. So here we will calculate P1 300 into x by 6, P2 as 400 into x by 4. So P1 is about to 50x, P2 is about to 100x. That means here the total load demand is 300 plus 400 means that will be 700. But here the total power is given with 600 megawatts. Here 50 and 100. That means total 150. P1 plus P2. 50x plus 100x. 150x equal to 600. X value we may obtain as 4. That means the load supplied by largest machine is 100 into x means P2 equals to 400 megawatts. That we are going to obtain as one of the P2 value. So with this session, we will consider some reference portions. So this may give us more information regarding this load frequency control area. And we will extend this analysis some more for coming videos. And we will discuss some analyzed problematics based on this load frequency control. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.